All right, let's talk about process synchronization. This is the hidden choreography that keeps our entire digital world from just falling apart. It's like a silent traffic cop directing billions of things happening every second inside our computers, and today we're going to see exactly how it pulls it off.
And to really get why this matters, think about this for a second. You and someone else are both staring at the very last seat on a flight to Hawaii. You both slam that confirm button at what feels like the exact same millisecond. So, who gets the seat? And how does the computer possibly make that decision without selling the same seat twice? The answer is at the heart of what we're talking about today.
You see, that whole mess we're trying to avoid, it's called a race condition. It's what happens when multiple processes all try to mess with the same shared piece of data at the same time. Since you can't ever predict the exact order they'll run in, the final result can get completely scrambled. It's a total free-for-all, and it's how you get corrupted data.
Okay, let's walk through this step by step to see just how bad this can get. We've got two processes. One is adding to a counter, one is subtracting. The count starts at 5. So, process A reads the value 5. But right after that, before A can do anything else, process B also reads the value 5. Now, process A does its math and gets 6. Process B does its math and gets 4. Then process A writes its result back, so the count becomes 6. But then, boom, process B writes its result back, overwriting A's work. The final count is 4. Wait a minute, we added 1 and subtracted 1. The answer should be 5. This is a race condition live and in action, giving us a totally wrong result.
So how in the world do we fix this? Well, we have to solve what's called the critical section problem. A critical section is just that little piece of code where the shared data gets touched. And to prevent a race, we need a strict set of rules, a protocol, that every process has to follow before it's allowed to enter that section.
All right, rule number 1, and this is the big one, mutual exclusion. It's actually super simple. If one process is inside its critical section, then no other process can get in, period. The best way to think about it is a single-person restroom with only one key. If someone has the key and is inside, everybody else has to wait their turn. No exceptions.
Okay, on to rule number 2, progress. This rule says that if the critical section is empty and there are processes waiting to get in, you can't put off the decision of who gets to go next forever. The system can't just freeze up. If the restroom is free and there's a line of people waiting, somebody's got to get that key. You can't just leave them all standing there.
And finally, rule number 3 is all about fairness. It's called bounded waiting. This just means there has to be a limit to how many other processes can cut in line in front of you while you're waiting. It guarantees that if you ask to enter, you will eventually get your turn. This prevents any single process from starving because it's stuck waiting forever.
Now, for a long time, some really smart people came up with these brilliant, purely software-based algorithms to enforce these 3 rules. And they were geniuses, but they all relied on one fundamental assumption about how computers run code, an assumption that, well, modern machines just threw right out the window.
Take a look at this. Simple, right? Thread 1 just sits there and waits for a flag to become true, then it prints out the value of x. Over in thread 2, it sets x to 100, and then it sets the flag to true, which should let thread 1 go. So what's it going to print? You'd think 100. I mean, it has to be 100, right?
Well, here's where everything gets turned on its head. To squeeze out every last drop of performance, modern CPUs and compilers will actually reorder your code's instructions if they don't depend on each other. To the CPU, setting X and setting flag are 2 separate things, so it might decide it's faster to set flag to true before it sets X to 100. The order you wrote the code in? Yeah, that's more of a suggestion to the CPU.
So what's the result of all this? It's a total disaster. Thread 1 sees that the flag is true, it breaks out of its waiting loop, and it prints the value of X before thread 2 ever got around to setting X to 100. So it could print 0 or just whatever random garbage was in that memory location. Your logic is completely broken. And this is the critical takeaway. On modern hardware, purely software solutions for synchronization just aren't reliable enough.
Okay, so if clever code on its own is broken, what do? We have to go deeper. We need to get help from the hardware itself. We need guarantees that are baked right into the silicon, rules that the CPU has no choice but to follow.
The first tool we get from the hardware is called a memory barrier. Think of it like this. It's an instruction that screams at the CPU. Whoa, stop! Do not cross this line. You have to finish every single memory operation I gave you before this point before you are allowed to even start anything after it. It's a hard line in the sand that stops that dangerous reordering in its tracks.
And then we have the real bedrock of all this, atomic instructions. These are special commands that the hardware guarantees will happen all at once, as a single, indivisible, uninterruptible step. A classic example is compare_swap. It reads a value, checks if it's what you expected, and if it is, writes a new value, all in one single operation that no other process can interrupt halfway through. These are the fundamental, unbreakable building blocks for everything else.
Okay, but let's be real. Nobody wants to be writing in atomic instructions all day. It's super complicated. So what happens is that operating system designers use these powerful hardware guarantees to build higher-level tools that are much easier for programmers to actually use.
So, the most basic and common tool you will see is called a mutex lock. And mutex is just short for mutual exclusion. It's literally our restroom key metaphor, but in software. Before you enter a critical section, you have to acquire the lock. If someone else has it, you wait. When you're done, you release the lock, and you hang the key back on the hook for the next person.
So a mutex is perfect when you have exactly one thing to protect. But what if you have, say, a pool of 4 connections to a database? For that, you use a counting semaphore. A mutex is one key for a private restroom. A semaphore is like a front desk with a rack of keys to a restroom that has multiple identical stalls. It lets a certain number of processes in at the same time, not just one.
So when you put it all together, you can see that process synchronization is really all about layers. Way down on the bottom, you've got the unbreakable guarantees from the hardware, like atomic instructions. Then, built on top of that, the operating system gives us useful tools like mutexes and semaphores, and that's what lets programmers write code that can handle all this concurrent chaos safely.
You know, pretty much everything you do digitally, from your bank account to your social media feed, it all hinges on these carefully designed rules for sharing. It's an absolutely incredible feat of engineering, and it kind of leaves you with this one last wild question. As we start heading toward bizarre new worlds like quantum computing, where just looking at something can change it, what will the keys and locks of the future even look like?